A ship moored alongside a dock looks calm and stable. From the outside, she appears completely still, as if nothing is acting on her at all. There is no forward motion, no sideways drift, and no visible rotation. To most observers, this looks like a static situation, almost trivial. From an engineering perspective, however, this calm appearance is misleading. The ship is not stationary because nothing is happening. She is stationary because several forces are acting on her at the same time, and those forces are being continuously balanced. Wind is pushing against the hull and the superstructure above the waterline. Currents are trying to drag the ship along the length of the berth. Waves are lifting her, lowering her, and applying cyclic forces that tend to pull her away from the quay. None of these forces disappear, and none of them cancel each other automatically. Instead, they are transmitted through the mooring system, into the mooring lines, through bollards and dolphins, and finally into the dock structure itself. This is why mooring design is not simply an operational detail. It is not just about tying a ship to a dock. It is a structural engineering problem, and at its core, it is a problem of force equilibrium. In this video, we are going to examine how mooring forces are calculated in practice. We will start with the environmental loads acting on the ship, and we will follow those forces step by step until they reach a single bollard on the quay. Every calculation of mooring forces begins with the same question: what external actions are acting on the ship while she is alongside the dock? The answer depends strongly on the type of port and its location. In most seaports, wind is the dominant action. Even when waves are relatively small and currents are moderate, wind can generate very large forces because it acts on a large exposed area above the waterline. In river ports, the situation is often different. There, the force of the current may control the design, especially when strong river flows act on large vessels for extended periods of time. In exposed locations, such as offshore berths or ports open to the sea, wind, current, and waves may all act simultaneously, and berth operations are often limited to specific weather conditions. Let us begin with wind, because in many practical cases, wind loading governs the entire mooring system.
Wind does not act as a constant force. Its speed varies with time. Gusts appear, and the response of the ship depends strongly on the direction from which the wind is blowing. For this reason, port engineering does not treat wind as a simple static pressure. Instead, a specific formulation is used to represent the total wind force acting on a ship moored alongside a dock. The total wind force acting on the ship can be expressed as the product of several factors that account for wind intensity, ship size, dynamic effects, and ship orientation relative to the wind. Written explicitly, the total wind force is given by the following expression. The total wind force equals a shape factor multiplied by the specific wind pressure, multiplied by correction coefficients, and multiplied by the projected wind areas weighted by the wind angle. Although this equation may look complex at first glance, each term represents a clear physical idea. When the terms are examined one by one, the logic behind the equation becomes much easier to understand. The first key term is the specific wind pressure. This term represents how intense the wind loading is, and it depends directly on the sustained wind speed. Wind pressure is proportional to the square of the wind speed. This relationship reflects the physics of moving air and the kinetic energy it carries. This squared relationship is extremely important. If the wind speed doubles, the resulting force does not double. Instead, it increases by a factor of 4. This is why extreme wind events, even if they occur infrequently, often control the design of mooring systems and port structures. In port engineering, wind speed is defined as a 1-minute average measured at 10 meters above the water surface. If wind speed data is recorded at a different height, it must be converted to the equivalent speed at 10 meters using a power law relationship. The next important consideration is ship size. Large ships do not respond instantaneously to short gusts of wind because of their inertia and mass. This effect is included through a correction coefficient that depends on the length of the ship, reflecting the reduced response of larger vessels.
In addition, a gust factor is introduced to account for the dynamic amplification caused by wind fluctuations over time. A shape factor is also included to account for aerodynamic effects, such as suction on the leeward side of the ship, which can significantly increase the total force. Wind does not act only on the hull. It also acts on superstructures, cranes, loading equipment, and any other elements located above the waterline. For this reason, projected wind areas are considered in both the longitudinal and transverse directions of the ship. The relative importance of these areas depends on the angle between the wind direction and the ship's center line. In many cases, the most critical loading condition occurs when the wind blows approximately perpendicular to the ship. When detailed ship data is not available, the exposed wind area can be estimated using an empirical relationship based on the ship's length. This approach provides a conservative but practical estimate suitable for preliminary design. Once the total wind force acting on the ship has been determined, the next step is to understand how that force is transmitted to the dock structure. The wind acts on the ship, not directly on the quay. The ship transmits the wind force through the mooring system. A typical mooring arrangement includes bow lines, breasting lines, springs, and stern lines, each serving a specific purpose. When the wind acts normal to the ship, the total force is distributed among the mooring points that are working simultaneously. For preliminary design, the normal force per bollard is calculated by dividing the total force by the number of effective bollards. In reality, this distribution is never perfectly uniform. Some lines carry more load than others, and some bollards are more heavily loaded. To account for this non-uniformity, engineers increase the calculated force by an additional allowance, typically on the order of 20%. Geometry now becomes critical. Mooring lines are inclined both horizontally and vertically, and this inclination has a direct effect on the tension in the line. Because of this inclination, the actual tension in a mooring line is greater than the horizontal force it is resisting. If a line forms a horizontal angle alpha and a vertical angle beta, the line tension can be calculated using a trigonometric relationship. From this tension, the longitudinal and vertical components of the force transmitted to the dock structure can be obtained. These vertical force components are particularly important because they affect the global stability and local strength of the dock structure. In practice, not all mooring lines reach their maximum tension at the same time, and many forces partially cancel each other out. This is why design guidelines provide recommended mooring loads per bollard, especially useful during preliminary design stages. Bollards located at the ends of a berth are usually designed for higher loads than intermediate bollards due to their critical role. In exposed locations, engineers often increase system flexibility using longer lines, nylon tails, and softer fender systems. Increased flexibility reduces peak forces and improves the overall behavior of the mooring system under variable environmental conditions. A well-designed mooring system does not eliminate environmental forces. Wind, current, and waves continue to act on the ship. What the system does is manage those forces, distributing them safely and limiting ship movements to acceptable levels. When mooring design is done correctly, operations remain safe, structural limits are respected, and the system performs as intended. Even when everything looks calm from the outside, a carefully calculated equilibrium is constantly at work, keeping the ship and the port infrastructure safe. If this video helped you, don't forget to like it. It really supports the channel. Subscribe for more content like this, and let me know in the comments what topic you'd like to see next. Thanks for watching, and I'll see you in the next one.